The complex number z is defined by z is equals to a plus iota b, where a and b are real. The complex number z conjugate is denoted by z conjugate. Show that modulus of z whole squared equals z conjugate, and z minus k iota whole conjugate is equals to z conjugate plus k iota. All right, let's get started. In part 1, we have to show that modulus of z when squared gives us the same answer as z and z conjugate. Okay, so modulus of z would be applying Pythagoras theorem on it. So it's just a squared plus b squared. So this will be a squared plus b squared whole squared. And then, oh, no, actually there's a square root here as well. When we find modulus, we apply Pythagoras theorem. So square root of a square plus b square. And that's what we're going to write, and then square it as well from this because of this square. Next is equals z times z conjugate. So z is a plus iota b, and z conjugate is a minus iota b. Okay, so the left hand side becomes a squared plus b squared, and the right hand side becomes a squared minus iota b minus iota ab plus iota ab minus b squared iota squared, so that's going to be another minus 1. So we're getting a squared plus b squared here as well. So hence proof left hand side equals right hand side. So we've proved that this is true. Okay. Next we have to prove that z minus k iota conjugate, let's write that down. Z minus k iota whole conjugate must be equals to z conjugate plus k iota. Okay, so z minus k iota would be a plus iota b minus k iota whole conjugate equals a minus iota b plus ki. Okay, so this would, if we write the imaginary and the real part separately, we get b minus k here, and whole iota whole conjugate should be equals to a plus k minus b iota. Okay, now when we conjugate this, we're going to change the sign of the real part, sorry, of the imaginary part. And are these two equal? Yes, they are. Let's just send the minus sign inside. So plus, this becomes k minus b bracket iota is equals to a plus k minus b iota. Hence, left hand side equals to right hand side proves that this is true. All right. Next part is, in an Argand diagram, a set of points representing complex numbers z is defined by the equation modulus of z minus 10 iota is equals to 2 times z minus 4 iota. Show by squaring both sides that this is true. All right, so since they're telling us to start by squaring both sides, let's do that. So we're going to square z minus 10 iota modulus equals to square the other side, so 4 times modulus z minus 4 iota whole square. All right, now how do we expand this? We will go back to the given proofs here and use these. Okay, so we know that when we whole square a modulus, we get z times z conjugate. So we're going to write z minus 10 iota times z minus 10 iota conjugate equals to 4 times, again same identity, z minus 4 iota times z minus 4 iota conjugate. Okay. Now we're going to use z minus 10 iota, z plus 10 iota. No, sorry, not z plus 10 iota. Now we're going to use the other identity given. This will be expanded using this, and this will be expanded using this, which says z minus k iota conjugate is equals to z conjugate. So we're going to write bracket z conjugate and plus ki. So plus 10i. Same on the other side. This will become z conjugate plus 4i. Okay, now we expand both sides and hopefully we'll get this in the end. So z times z conjugate plus 10 iota z minus 10 iota z conjugate minus 100 iota square. So that's going to be minus 100. So I'm writing plus 100 here equals to 4 times z conjugate plus 4 iota z minus 4 iota z conjugate and minus of 16 iota square, that is iota square is -1, so we get a plus, minus and minus becomes plus 16. Okay, now you're going to open the brackets on the right hand side and then rearrange this. I'm doing this in one step. We will get 3z conjugate plus 6 iota z minus 6 iota z conjugate minus 36. Okay. Now we can divide both sides with 3, so we get 0 equals z conjugate plus 2 iota z minus 2 iota z conjugate minus 12. So we have shown that we get this. Hence shown. And I think it would be better if we swap the places of these two because that's how it is here. So swap these places. This becomes negative 2iz conjugate and this becomes plus 2iz. Okay, that's done. Okay, next part. Hence show that z minus 2 iota is equals to 4. Again, we're going to start by squaring both sides. Z minus 2 iota whole square equals 4. For whole squaring, we're going to use this. Z in one bracket and z conjugate in the other. And we have to show it would be equals to 4. Okay, so again, this will be expanded using this, which is z conjugate plus 2i. We should get 4 here. Okay, let's expand z times z conjugate plus 2 iota z minus 2 iota z conjugate and minus 4 iota square, which would be plus 4 equals 4. Now hold on, after squaring both sides, we should have gotten a 16 here. I forgot to square the right hand side. All right. Now notice that This is equals to 12 from here. If you make this the subject and move minus 12 to the other side, you get a 12. So this becomes 12 plus 4 equals 16. 16 equals 16. So hence this must be true. Z minus 2 iota equals 4. So there was a 16 here as well. This must be true. Z minus 2 iota modulus is equals to 4. Okay. Part 3 is describe the set of points geometrically. Okay. So what is this? We can see that it is a circle. Let's take Z common because that's the convention. Become 0 plus 2 iota equals 4. So it's a circle with center 0, 2 and radius equals 4.